So now I want to figure out what the pH is in my titration of benzoic acid with potassium hydroxide after I've added 25 milliliters of 0.1 molar potassium hydroxide. So I'm going to do that calculation down here. And it's going to be awfully similar to that last calculation that I did. So I have added 25 milliliters, or 0.025 liters, of 0.1 molar potassium hydroxide. So that's moles of hydroxide per liter. That's going to be equal to 0.0025 moles of hydroxide that I've added at this point. Now, the equation that is happening is still the same as it was in the part B of this example. I have benzoic acid, and it's going to react with the added hydroxide to make water and the conjugate base, benzoate. So let's see what happens using an ICF chart, looking at the initial concentrations and going to the final concentrations here. I don't want to use concentrations because it's just easier to use the number of moles for these titration calculations. So I'm just going to plug in the original number of moles of benzoic acid that I started with, and then alongside it I have the number of moles of hydroxide that I'm adding. Now you can see that this number is still bigger than this number. That means that I have enough benzoic acid to consume all of the added hydroxide. And effectively here, I'm cutting my number of moles of benzoic acid in half. All of the hydroxide gets consumed, so I don't have any of it left. Water, I don't care about it, because it doesn't influence the pH of the solution. And the benzoate now is going to be increased by 0.0025 moles. So I'm going to end up with 0.0025 moles of the conjugate base. So again, this is a situation where I have in solution a weak acid and its conjugate base. That is, once again, a buffer. And that means that I can use the Henderson-Hasselbalch equation to calculate the pH of it. So the pH is going to be equal to the pKa. You may remember from the last problem, part B, that the pKa is the negative log of 6.3 times 10 to the minus 5, or 4.2. So 4.2 plus the log of, we can plug in the number of moles of base over the number of moles of acid. And that we can use the number of moles because the total volumes would cancel since this is a ratio. Aha! What do you notice about this? What is the log of 1? Why, the log of 1 is 0, of course. So the pH here is equal to the pKa. This is a very special point in the titration. The pH being equal to the pKa is known as half equivalence. What that means is that we are halfway to the equivalence point volume-wise. We have added half of the number of moles of hydroxide that we need to get to equivalence. So whenever we're halfway to the equivalence point, the pH is going to be equal to the pKa of the acid. So I'm going to go up here and put that data into the chart that I'm maintaining. So I have a pH of 4.2. The number of moles of benzoic acid is equal to the number of moles of its conjugate base. And again, that is a characteristic of what we call half equivalence. Okay, so I'm just abbreviating that there. Now, let's go to 48 milliliters of potassium hydroxide added and see what that calculation looks like. So I'm going to go down here, and this is part D. I have added 0.048 liters of the 0.1 molar KOH. That is going to be equal to 0.0048 moles of hydroxide that I've added. So if I look at how that reacts with the benzoic acid, of course that reaction goes to completion to make water and the conjugate base. And if I make an ICF chart, starting with the original number of moles of benzoic acid and the number of moles of hydroxide that I'm adding, I can see that the values are getting more similar. I still have enough benzoic acid to consume all of the added hydroxide, but look at this, I'm getting low on benzoic acid, right? It's starting to run out. It's starting to be mostly consumed by the hydroxide that I've added thus far. And as a result, on the product side, the number of moles of benzoate is, as we can see, greater than the number of moles of benzoic acid at this point in the titration. Is it still a buffer? You bet it is. I still have the weak acid and its conjugate weak base. And as long as I have both of them present in solution, it's still a buffer, and I can still use the Henderson-Hasselbalch equation to figure out its pH. Okay, so as long as I still have both of those in solution, I can calculate its pH using Henderson-Hasselbalch. So that's going to be 4.2 plus the log of the number of moles of base over the number of moles of acid. So now the tables have turned, and I have more base than I have acid. So that means that this term is going to be positive. And if you figure this out, it comes out to be above the pKa value. You should get a value of 5.6 for the pH here. So let's put that into the chart that I'm maintaining up here. I have a pH of 5.6. Oops. Just to not be annoying with the color, I'm going to try to be consistent. I have a pH of 5.6. I have fewer moles of benzoic acid than I have moles of benzoate, the conjugate base, at this point in the titration. So now let's examine what the pH would be after I've added 50 milliliters of 0.1 molar KOH. So this is going to be calculation letter E. I'm going to do that down here. I have added 50 mils, or 0.05 liters, of the 0.1 molar KOH. So that is 0.0050 moles of hydroxide that I've added. And you can probably guess what's going to happen here. Think about that hydroxide reacting with the benzoic acid to make water and benzoate. Going to make that ICF chart. So I started out with 0.0050 moles of HA, and I've added 0.0050 moles of hydroxide. So as you can probably tell, this is the equivalence point. I have added just enough hydroxide to wipe out all of the acid. No more than that. Okay, so this is the definition of equivalence point. I've added just enough of the strong base to wipe out all of the weak acid. And what that does on the right side is it basically has transformed all of the weak acid into its conjugate base. So now I have 0.005 moles of benzoate. So what kind of solution is this? It's clearly not a buffer anymore. I don't have any more weak acid, so it's not a buffer anymore. All I have in solution now is weak base. so now we need to go back to chapter 13 because this is a weak base calculation at this point in the titration. It's a standard weak base calculation. You could go back to chapter 13 if you needed a refresher on how to do that. If we write a base hydrolysis reaction and do an ice chart and everything, you're going to find that the hydroxide concentration is going to be equal to the square root of the Kb times the initial concentration of the weak base or the benzoate. This is definitely a safe assumption because the Kb is going to be very, very small, and as long as 100 times Kb is less than that initial concentration, this is a safe assumption. So let's calculate both of those, the concentration of the weak base. We know that we have this many moles of it, so I'm going to take that as the numerator and then put that as over the total volume. So I have 0.0050 moles of the weak base at this point in the titration. And the total volume should be 100 milliliters. And the reason for that is I've added 50 milliliters to the original 50. So the total volume of my solution should be 100 milliliters or 0.1 liters. So the concentration of weak base should be 0.05 molar. The Kb I need to obtain from the Ka. Of course, Kb I can get from Kw over Ka, or 1 times 10 to the minus 14 divided by the Ka, which the problem gave me as 6.3 times 10 to the minus 5. So the Kb value should be 1.6 times 10 to the minus 10. So that's pretty good evidence that the assumption that I can not use the quadratic equation is legit because this Kb is really tiny. So 100 times Kb is going to be way less than 0.05 molar. So that means I can use this equation to figure out the concentration of hydroxide and then calculate the pOH and then get the pH from there. So using that equation, the hydroxide equals the square root of the Kb, so that's 1.6 times 10 to the minus 10, times the concentration of weak base, or 0.05 molar. If you do that, you should get a value, after you take the square root, of 2.8 times 10 to the minus 6 molar. That's a molar concentration of hydroxide. You can take the negative log of it, and you should get 5.6. And then, of course, subtracting that from 14 minus 5.6, you should get 8.4. Wow, so that is a basic pH. And you can see that it's a weak base calculation. You can see how the pH has shot up at equivalence compared with what it was before. So going back to my data chart, I have a pH of 8.4 at equivalence. I have wiped out all of my weak acid, and all I'm left with at this point in the titration is the conjugate base. Okay, so in the next video, we'll go beyond the equivalence point in the titration. Let me just label this as equivalence point. Thank you.